Okay, so there's a lot of ways to do factor polynomials and come up with your zeros. And the textbook certainly shows some ways to do this. I mean, you have some tests that talk about limits and bounds and then all the rational root theorem where you can come up with possible rational roots, and those are all great. This is 2020 when I'm recording this, so I don't know. I don't know how useful some of that stuff is. So I'm going to show you if you can do this, I figure you understand this material. Okay, so I've got this polynomial. It's a third degree polynomial. I've got to factor it. I got to find it zero. I got to find all zeros. Okay, and so one thing we can do is I graphed it out in Desmos, and some things I'm noticing about this graph is, let's see, let me get a pointer going. I see it crosses the x-axis 3 times, and we know about the fundamental theorem of algebra says we take a look at the degree of the polynomial, the biggest exponent, and that's how many zeros are there. So I see 3 zeros, so we've got it, and these all look like nice integer values. Well, that's not an integer, but that's a nice rational value, right? So if you think about, we'll talk about the rational root theorem and how it supports this. Well, the rational root theorem says you take a look at the last term and the coefficient of the first term, the leading coefficient, and your possible rational roots are factors of all of these. So negative 12, I could think about negative plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus, 12? And then the denominator, plus or minus 1, plus or minus 2. Those are all possible zeros. And then I'd have to list them all. One of the my open math assignments is going to be, can you list all the zeros? Well, they can be all of these. So like 1 over 1, and 2 over 1, and 3 over 1, 4 over 1, 5, 6 over 1, 12 over 1, plus or minus. And then I could do 1 over 2. Here, I'm going to do a little bit of writing here. I see I could have plus or minus 3, right, for the first one. Or I could do plus or minus 1/2, because it's 1 over 2. And the other one could be plus or minus 4, right? And those are 3 of the possible zeros. And of course, we just looked at this graph a second ago, and you can see negative 3, negative 1/2, and positive 4 are the exact zeros. So do you see how the rational root theorem gives you a list of all that you could do? Now, if you didn't have graphing technology, that's why they had to develop all those old methods. Now, a couple of things we could do. How do I know that this graph isn't going to turn around and cross up again there, or same thing down there? How it could turn around? Well, I know that the ending behavior of an x when the leading coefficient is positive and the degree is 3, I know the ending behavior for this function. You studied this back in the last section, or a couple sections ago. As x goes to negative infinity, I know y goes to x goes to negative infinity, y also goes to negative infinity. So this is not going to turn around. This can't turn around. And then as x goes to positive infinity, y also goes to positive infinity. And so again, that can't turn around and head back down and give me another 0. So I know these are the only 3 zeros. So if they ask me to factor this polynomial, here, let me stop this and clear up some stuff. Since I know x equals negative 3 is a 0, I know that x equals negative 1/2, and I'm going to write that as a fraction. And then x equals 4 is also a 0. How do I get the factors out of that? Well, remember, these became zeros because x plus 3 has to equal 0. We know that x plus 1/2 equals 0, and x minus 4 has to equal 0. And so there's factor. There's factor. Some people will write the factor of x for the x equals negative 1/2, 0 is x plus 1/2. It's not really the best way to do this, because if you were to do some factoring, you would by hand, the old way, what you would have done is you would have divided by 2 and then added 1. So think about it this way. This is going to become 2x plus 1 equals 0. And then that's the better way to write the factor. Okay. So what are the factors of this? So this polynomial factors to x, let's see, x plus 3 and 2x plus 1 and then x minus 4. Now, I'm only writing it this order because sometimes, myope math's a little picky like that. For us as humans, it's really not a problem. So let's do some erasing. And if I were to expand that all out, I would come back up and I would get that original function. Okay, so there are the factors. We've got the zeros. Now, the only other thing that I'm expecting, and for this one, I would have a hard time defending saying you didn't show me that, you did the graph, you gave me the graph, you said here are the zeros, here are the factors. You didn't verify this analytically. Well, I would argue, you could argue with me that said, well, there's nothing due here because I can see the zeros. I know there's nice integers. There's not much going on there. So with that said, this is a pretty easy question. Let's kick it down the road a little bit with the next one. What did I just do? Oh. So I see a 4th degree polynomial. Here, let me get a pointer going. 4th degree polynomial, and the leading coefficient positive. So I know the ending behavior for this polynomial is going to look something like this. As x goes out to negative infinity, y goes out to positive infinity, and as x goes out to positive infinity, y is also going to go out to positive infinity because it's an even degree polynomial. And that's what I'm seeing here, right? It's heads up this way. That's not going to turn around and give me another 0. So I also see, when I look at this graph, 4 zeros, I mean. So that confirms the fundamental theorem of algebra. It says, take a look at the degree. This should be 4 zeros, and that's what I'm seeing. However, for these, I see a rational 0 of -3. I see a rational 0 of -1/2, just like in the last polynomial. But then I get these decimal values. Now, maybe those are rational, but maybe not. And you know that I said this was going to be different, so you know it's not going to be. So here, how do we deal with this? How do we find those zeros? Because we want to be able to factor this thing. So here's what you're going to do. Now, I see that -3 is a 0, so I'm going to use synthetic division to get rid of that, remove that. I don't want this to be a 4th degree polynomial because I don't really know how to deal with that. So as you did from the lessons, or if you look in the lessons, or you did this back in Algebra 2 or college algebra, you learned about synthetic division. And it's just a way to divide polynomials that's a little abstract, but it's much quicker. So I guess I'll talk you through a little bit of this. So you put the 0, not the factor. You got to set it equal to, remember, the factor for this one would be x plus 3. And when you do synthetic division, you want the actual 0. So -3 is what I wrote here. And then you just pull the coefficients off each of the terms. If you're missing a degree, you have to stick a 0 in there. I'm not sure I did any of those. I'm not sure I did any examples with missing degrees, but there are plenty in the book where you can do that. So I brought down the 2, and I always drop an arrow down there as just a reminder that that's what I'm doing. And you multiply. You take this times this, write the product here. So that's -6. Then you combine them, so that's 3. Then you repeat the process. 3 times -3 is -9, and that's -7. And then -7 times -3 is +21. That gives me what? That gives me -4. And -4 times -3 is +12, which is 0. We knew the result was going to be 0 because this was the 0 for the polynomial. And the remainder, remember, if this is 0, go take a look at those lessons, and you can certainly find this out at Khan Academy or out on YouTube. If the remainder is 0, we know it's a factor. We know it's a 0. So what I've got right now is I've got x plus 3 times 2x to the third plus 3x squared minus 7x minus 4. So I've got this polynomial factored down this far, but this is still a third degree polynomial, and that's still, you know, weird. I can factor second degree polynomials easy. Third degree, they're a little weirder. But fortunately, they gave me another 0. This function has another rational 0 of negative 1/2. So I'm going to come back into this, and I'm just going to extend. I mean, I could set up another whole synthetic division problem, but why don't we just do this? So I've got negative 1/2, bring down the 2. 2 times negative 1/2 is negative 1. That gives me 2. 2 times negative 1/2 is negative 1. That gives me negative 8. Negative 8 times negative 1/2 is positive 4, which is 0. We knew it was a 0 again, right? Now, this is the one issue with synthetic division, and I don't have a good answer for this, folks. I've asked people that know much more about math than I do, and they couldn't give me a good answer too. I don't know why this happens. But when you divide by you remember how I wrote the factors right here from this? Well, see how these have a common factor of 2? Well, that comes in because we divided by 2. So what you want to think about doing is, I've got a GCF that isn't really here, but it got introduced by the division. So really what I've got is, I've got the x plus 3 factor. I've got that 2x plus 1 factor, remember from the last video. And then what I've got here, I've got 1x squared plus 1x minus 4. Do you see how I took care of that 2, that extra 2, that common factor 2? Well, that 2 wasn't in the original. So I took care of it by pulling those numbers down and making them smaller. So now what I want to do is I got to find those other 2, those must be irrational zeros that are there on the graph, okay? So here's what you do, is I've got a quadratic equation, and you know of quadratic equations, we solve them. What we're really doing is we're trying to solve the equation x squared plus x minus 4, where does that equal 0? Well, that won't factor, so I could complete the square, use the quadratic formula. I'm going to choose to use the quadratic formula. Let's see if I can just slide this whole screen up. I think I can. Maybe I can't. Oops, I can slide that up. Can I slide that up? Yeah, okay. Let's see if I can slide this up. I can. And remember the quadratic formula you did back in section 2. So negative b is negative 1 plus or minus the square root of 1 squared minus 4 from the formula times 1 times negative 4 all over 2 times a, which is 1. So that's what x is equal to. So that gives me negative 1 plus or minus the square root of 17 over 2. So if I went and grabbed a calculator, I would suspect that if I did negative 1 minus root 17 over 2, that would be where the negative 2.562 is coming from. And negative 1 plus the square root of 17 over 2, that's where they're getting the positive 1.562 from. Okay, so that's finding all zeros. This is fully factored. I can't, this is the fully factored polynomial. I can't factor that anymore. And I've got my zeros of negative 3, of negative 1/2, and then plus or minus, or I guess since I wrote them all out, I could do that. Those are the exact values. Okay. If the problem or I ask you for an exact value, this is what I'm looking for, this won't cut it for me. Okay, you got to be able to do this analytically. So here's another 4th degree polynomial. I graphed it. Here, though, what's different about this one is I'm seeing that it heads up to positive infinity, just like a 4th degree polynomial should with a positive leading coefficient, but I'm only seeing 2 zeros. So that tells me there's going to be 2 imaginary, 2 complex zeros. We had 2 irrational last time. Now we're going to get 2 complex. And I think this is section 6 in the textbook, 3.6, where they talk about complex zeros. So it's very similar to what we just did. I know I have zeros of negative 3. I know I have zeros of negative 1/2. So let's just do some synthetic division with this thing. So let's see, negative 3, and we're going to do 2, 7, 11, 28, and 12. So 2, that gives me negative 6, which is 1, which is negative 3, which is what, 8. 8 times negative 3 is negative 20. Somehow I jumped. Okay, so then we got let's see, where was I? Negative 24. That gives me 4. We multiply and we get negative 12, which is 0. We knew that. So I know I've got an x plus 3 factor. And now let's take care of the negative 1/2. So that's 2. That's negative 1, which is 0. That's going to be 0, which is 8, which is negative 4, which is also 0. So I've got, and remember how I've introduced that extra 2, that common factor 2, and we'll just won't worry about it. So this polynomial factors to x plus 3 times 2x plus 1 times x squared plus 4. So that's the polynomial fully factored. Here's one real 0, here's the other real 0. So this will have to be 2 complex zeros or 2 imaginary zeros. So what we're doing is, we could use a quadratic formula, but because this is just x squared plus 4, it might be easier just to extract the square root. So I'll subtract 4. And when I take the square root of negative 4, remember you have to deal with the i's. So I have plus or minus 2i as my other 2 zeros. So I've got the factors. The zeros are x equals negative 3, x equals negative 1/2, x equals negative 2i, x equals positive 2i. And we've satisfied the theorem. Here's my 4 zeros. Okay, so for this exercise, this practice problem, one thing I made an error on when I wrote it, I had a 6 here. You should change that to a 12. I had in the graph, I messed it up when I copied it over. So that has to be a 12. Change that to a 12. So I graphed this, and I see 2 zeros. So it must be 2 must be imaginary, so another variation on that. This 0 at negative 1/2 looks like it might have a multiplicity, of 3. I don't know if it does. Actually, I don't think it does, because I remember when I made the problem. But we'll check it, and we'll see. We'll pretend I didn't know that, and we'll check and see how to eliminate that as a possibility. All right, so what I'm going to do, I'm going to run my synthetic division through again with negative 3. So we'll get rid of that. So negative 3, and we'll do, 2, 9, 12, 10, and 3. And that's 2, and with that, negative 6, and that's 3, and that's negative 9, which is 3. Here's where I had messed up. I knew it wasn't working. And that's a negative 9, and that's 1, and that's negative 3, and 0. So I know it's 0. I know it's a root. So then I know negative 1/2 is also a 0. So let's get rid of that. So what's that? Negative 1, which is a 2. 2, which is 2. That's negative 1, which is 2, and that's negative 1, which is 0. Now that whole question about multiplicity. If I have negative 2, if I think it might have multiplicity 2, let's go ahead and do that. So that's 2 times negative 1/2 is negative 1, which is 1. And 1 times negative 1/2 is negative 1/2. So do you see how that doesn't cancel out? So that tells me that's not, it doesn't have any multiplicity. It's negative 1/2 it only has multiplicity 1. So if it had been working on it, I mean, if it had worked, I would have been surprised, because I know I didn't use that. That would have meant I multiplied it wrong when I expanded it. So how does this factor? So this factors to x plus 3. Remember, I changed the sign. And then the 2x plus 1 again. And then I've got that common factor of 2. And so we know those aren't really there. So x squared plus x plus 1 equals 0. So that's fully factored. This isn't going to factor. There's no way I can multiply and get 1 and have the products, have the two products sum to positive 1. So I know that's not a possibility. So I'll have to use the Pythagorean theorem. And the quadratic formula. So x equals -1 plus or minus the square root of 1 squared minus 4 times 1 all over 2 times 1, and so -1 plus or minus the square root of 1 minus 4 is -3 over 2, and of course you want to get rid of the negative underneath square root, so -1 plus or minus I root 3 over 2. So those two zeros are what? -1 minus I square root of 3 over 2, and -1 plus I square root of 3 over 2. So there's 1 0. Here's another 0. We had the x equals -3 as a 0. We had the x equals -1/2 as a 0. Here's the 4 zeros, okay? So not quite so slick because we had to use a quadratic formula for this one. So then, and the textbook has a number of ones like this in the section. I don't know if it's section 5 or section 6, but I'm graphed this 4th degree equation. It never crosses the x-axis, so I don't have the ability to use synthetic division to cancel out anything of them. So that tells me there's going to be 4 real zeros. Descartes' rule of signs is mentioned in the textbook. I don't know if I even want you to even think about it. So then I have to have a different way of tackling this. And then what I'm noticing I see a trinomial, and if this were x squared plus 5x plus 4, that would factor pretty easily to x plus 1 and x plus 4, wouldn't it? Well, this is a quadratic in form, and if we treat this as x squared, what you can do what's called a u substitution. You can say, hey, u equals x squared, so then it would be u squared plus 5u plus 4, and then you could factor it to u plus 4, u plus 1. That would give you the positive 5 in the middle. So then really, that's just back to here, okay? So when does this equal 0? Well, let's see here. Let me do a little erasing. And I'm just going to think about, I know they're imaginary roots or complex roots, so let's see what happens. If I have x squared plus 1 equals 0, doesn't that give me x squared equals -1? So x equals plus or minus square root of -1, which is I. And this is x squared equals -4. So x equals plus or minus the square root of -4, right? Which is going to be plus or minus I square root of 2. Oh, sorry. Plus or minus 2I. So there's my 4 zeros. A negative I, negative 2I, negative I, positive I, positive 2I. And it says there's 4 zeros, and I found them. Just happens none of them are real, so. And that's, this slide 5, so that's kind of what happens. And this is all if you can do this, I'll be happy. And I'm going to get asked this on a quiz and on an exam. So, make sure you learn how to do it. Get plenty of practice.